The first section in this chapter was really historical. It talked about Carnot and Joule, and it gave you a little introduction to the electrostatic energy for ionics. As we proceed through the chapter, we're going to introduce you to chemical thermodynamics. Now, many of you are going to want to go further, but in Chemistry 1210, Chapter 5 only deals with the first law, which is basically a tracking of energy changes. So, First Law of Thermodynamics, please do the homework. It's the only way to understand this conceptual chapter. We have some terms. The first one is system, and that's the portion singled out for a chemical equation. It can be an open system, like a pot of boiling water. It can be a closed system, like a gas in a cylinder, or it can be a thermos, like an isolated system. But what we're going to talk about is the system being the chemical equation. We're going to use the term surroundings, and the surroundings is everything else, and that will be the container that contains our chemical process. I'm going to develop this as we work through this section. So for now, you can look at it, but we're going to talk about it, okay? Let's start with work. We have to talk about work and internal energy. Work physics is force times distance. So if we're going to talk about internal energy, we have to include the term work. Internal energy is symbolized by the capital letter E, and it's the sum of the kinetic and the potential energies of a substance. That substance could be a molecule or an ionic material. We're going to talk about the change in internal energy, and that's going to be whatever is the final energy minus the initial energy. We're going to talk about Q, which is heat, and W, which is work, and we're going to say that internal energy is the sum of Q plus W. To make it real, what I've used is an example of our laptop batteries. Now, when you use your laptop, it releases heat. Maybe you felt it if you've kept it on your lap or put it on a table, and it also does work. So if I were to calculate the internal energy for my laptop, it is releasing 35 joules of heat. It is doing 250 joules of work for a grand total of minus 285 joules, and that would describe the internal energy of my laptop. Well, we're going to be working instead with chemical processes. So we're going to have some sign conventions for Q and W and internal energy. I put the table from the textbook at the top, but what I want to say is anytime we have a positive Q, that's a gain of energy. A negative Q is a loss of energy. A positive W is work done on a system. A negative W is work done by a system. So when you do the algebraic processes, if you come up with a positive delta E internal energy, it is a net gain. If you have a negative delta E, it is a net loss. So if we have a positive Q or a positive W, in both cases, there will be a net gain of energy, internal energy of the system. Please do some problems. I could do them, but I've learned over time a student needs to have to sit down with the actual examples and think their way through. So, what else do I want to force you to think about in this section? Well, there are processes that are called exothermic and processes that are called endothermic. When we have an exothermic process, heat is one of the products, and if you look at the example of potassium and water, when you toss it in, it is a very exothermic reaction. If we were in class, I would be doing it for you. So that giving off energy, seeing that heat, that is an exothermic process. If we have an endothermic process, heat is a reactant. And here our example starts with a solid making a solution. It starts at 23 degrees centigrade, and if you read the thermometer, it goes to minus 11 degrees centigrade. It is absorbing heat. Heat is a reactant, and that is an endothermic process. Now, I didn't really force you to look at any equations. I just want you to see the difference between exo and endo. What is just a regular equation, and what would be a process that you could observe. As we go deeper into this chapter, we'll be developing more conceptual ideas. So Thinking a little deeper about that idea of internal energy, it is the sum of all the kinetic and potential energy of all the particles that will make up a substance. It's kind of hard to wrap your head around, and we're not looking for depth here. We're just looking for an introduction. So we're going to be focusing on delta E is E final minus E initial. And here we have one of the pictures of your book where we say the initial state is hydrogen and oxygen, the final state is water, and if we were class, I would be exploding a balloon. You would see you'd hear a big noise, you'd see a flash of light. This is where energy is being given off, and by convention, when energy is released, it is given a negative sign, okay? The picture on the right, it's kind of, to me, I don't know why they didn't make two of them. Along this x-axis, they say this is the initial state of a system. If the final state is lower, as the example on the left, internal energy is lost to the surroundings, the internal energy decreases, and delta E is negative. If I look on the right-hand side, so I'm kind of going to draw a line right here. If I look at the right-hand side, I see my arrow is going in the upward direction. That says that energy is being gained from the surroundings, and that will be giving me a positive delta E. Now, I've taught this a number of times, and it's nothing at all like chapters 1 through 4. Science has many parts to it. Some are very conceptual, some are very methodical. But these would be the facts you need to know in order to solve more in-depth problems in this chapter. Almost done. Here, I'm going to draw one more picture. If I say energy is on the y-axis and I put an initial state and a final state, well, here we have saying we are given off heat. That means, according to the conventions taught here, we would draw an arrow pointing down. We would put our reactants, which are methane and oxygen, going to form our products, which would be CO2 and water. It's the combustion reaction from chapter 2. Notice the different ways to describe it. Negative delta E, E initial higher than energy final, delta E less than 0, that's the previous slide. Or we could also say the system loses energy to the surroundings. Now, I am convinced this is what makes Gen Chem very challenging, because one thing may be described in so many different ways. That is for an exothermic reaction. What if I have an endothermic reaction? Well, in that case, my energy, my delta E, is going to be positive. I would be drawing the arrow going in the up direction. I would say my energy final, which would be my products, is greater than my energy initial, which is my energy of reactants. I could also say all these things. Energy final greater than energy initial, delta E greater than 0, or system gains energy from the surroundings. Take some time to absorb this material. It will help you tremendously as we proceed through this chapter. I know I've thrown a lot at you, and if it is your first time, it's not a matter of rereading your notes. It's a matter of sitting down with your notes and challenging yourself. When you do those homework problems, it's going to make you think about what does all of this mean, and that's the goal of this course, is to have insight. Well, really, this section was challenging. I think it was challenging conceptually. It talked to you about something brand new called a state function. And a state function only depends on a current state of a system. It's going to be independent of how that state was prepared. So I'm going to use a different example. I'm going to say, how long does it take for you to fly to Denver versus drive to Denver? You right away will say, hey, the time is going to vary. I can do it in the air in a couple hours. It's going to take me at least 2 days to get there from Ohio. But in terms of a state function, there would be absolutely no difference. So what I'm trying to make you understand is that a system, if it's changed from one state to another, that state function is independent. You heard about one state function so far in this chapter. You heard about the state function internal energy. It is not the only state function, but a state function depends only on the initial and final, and I'm just going to say it's the physical states. Are we a solid? Are we a liquid and a gas? And that also is going to be developed in the year of Gen Chem. So you're going to see there are 4 state functions where we just talk about initial and final state, and there are 2 that are not state functions, and they were addressed in this section, Q and W.